All right, well, welcome to another STEIN Fireside Chat. I'm Bryan Klassen. This is Kai Miller. And today we have the pleasure of interviewing Cameron McIntyre, who's really needs no introduction. He's kind of a legend in the field of DBS, particularly when it comes to field modeling. And it's our pleasure to have him here from Duke. And we have, as usual, a Stein that he's going to take with him back. So thanks for being here.
Thanks. Happy to be here. It's great being, I've known Kai for forever, and it's great getting to know you, and yeah, looking forward to talking. So,
be interested to hear a little bit just about kind of what got you into this field in the first place.
Yeah, I was, as a graduate student, I was basically working on the physics of electric fields and neural activation, and it was very basic science-y, but I wanted to be a more clinically relevant kind of scientist, and so this was in the late 90s, and at that time, deep brain stimulation was kind of really getting off the ground clinically, especially in America. Kind of the first American cases were starting to be done, and I was like, oh, this is it. Like, I could do this. So I went and did a fellowship at Emory and learned, kind of like more like the clinical practice of DBS. And that then, gave me ideas of, oh, wow, we could build like these patient-specific stimulation computer models and then have them be, predictive tools to use for programming or surgical planning or whatever, right? And so that's how that all kind of got started.
Got it. Did you have a lot of competition back then, or were you just sort of the pioneer in this?
Yeah. There was no competition. So actually, there was a guy at Medtronic. His name was Roy Testerman. He was actually the very first person to ever build a finite element model of, kind of a DBS electric field. And he and I had met at a conference, and he was a super intelligent, super smart engineer guy. The added special sauce that I could bring to the table was more the neuron biophysics, right? So there's the electric field side of things, but then there's also the neural response characteristics. And I kind of, he and I, I think we were peas of the same pod kind of thing, but then I was able to kind of take it a little bit further in terms of clinical, kind of applications.
And your earliest models, I assume they're simpler than kind of what's come about.
Yeah.
What all did they take into account at the tissue level?
Yeah, so we work on, so there's, let's call it the clinical practice, kind of implementation that is primarily focused on predicting the spread of stimulation of axons around the electrode. And that's really what the core of what people now call the VTA or volume tissue activated. It's really about, kind of axonal spread of stimulation, but a pretty simplified approximation. But then on the science side, we can go, into super, super detail about, kind of the nuances of how, neurons, cell bodies, dendrites, complex axonal arbors, all these kinds of things. And so there's always this big range of, kind of the simple, straightforward thing that can be relevant to a clinical, kind of analysis, and then the 2025 science of like, what do we think we're doing with these stimulation, parameters or these stimulation, kind of new strategies.
Yeah. Okay.
So there's a phrase, all models are wrong, but some are useful, right?
Yes.
Your models are very useful, right? So we use them. Plenty of other neurology, neurosurgery teams use them around the country. And for that reason, you're, a celebrity in the deep brain stimulation world, right?
Okay. Yeah.
Well, I mean, I've seen you in Korea, I've seen you in England, I've seen you in Germany, I've seen you all over the US.
The career that I have had the opportunity to have is, unbelievable.
Yeah.
And I'm very appreciative, I don't take it for granted. But, let me tell you, in 1999 or whatever, that was not the goal. That wasn't the expectation or the aspiration or anything. It just happened. So, yeah.
Yeah. So, this is a slide that Bryan actually made, and I show this to a lot of our patients. And what I say to them is, this is the magnified version of a lead of one of the DBS leads. And it's got the top part, it's got the bottom part, and it's got these segmented levels. And there's a part we want to stimulate in green, a part we want to avoid, and it's in orange. And then we can basically direct the current through the different pads in order to more or less omit directions of stimulation that we want to avoid. This is how we explain things to patients. I think it's very useful for us. It's also very useful, I think, and actually, he does all the work when it comes to programming these things.
Yeah, sure.
And so sort of move the current distribution around. And this is my understanding of how we do electrical stimulation when we plan and try to get around side effects and move things up and down. And now, of course, some of the companies have much more, with their leads that have a lot more context. These models are still sort of balls of current moving around. How similar is this to the way that you thought things should work when you started translating it?
I mean, so this is exactly what the vision that Chris Butson and I, had. And, so this kind of have to fast forward up to maybe the early 2000s. 2004, I think, was kind of like when the original patents were submitted on this kind of stuff. And
was he a grad student?
No, so Chris did his PhD at University of Utah, and then his postdoc. He was really the first person I hired as a first year faculty member.
Okay.
I was working at the Cleveland Clinic at the time, and but Chris and I knew, like, okay, this is this is what we're going to try and do, and we're going to try and build this prototype, and let's see if we can do it.
Yeah, and Utah, of course, is sort of the birthplace of a lot of the best bioengineering applications that make it into patients, right?
Right. So I was going to either take a job at the U or the Cleveland Clinic, right? Those were kind of like the two jobs I was considering at the time, so that's how I met Chris, was when I was out there interviewing, and then ended up, I thought like the clinic was going to be a better fit for what I wanted to accomplish scientifically. And so, I was able to recruit Chris to come with me. So
nice. So you stole him from Utah.
Exactly. Yes. He ended up going back there. He was a faculty member there for 10 years probably after I think after he left my labs.
Yeah. And I think he still spends some time there, even though he was primarily at Florida.
Exactly.
Yeah. Cool. Do you still interact with him?
Oh yeah, all the time. I mean, just socially. Like, we haven't had a collaborative project for a long time, but not for any bad reason. Just
When I target for all the standard targets, I'm not aiming for white matter. The models that you have are mostly related to, you said stimulating axons, but you mean axons like as they come out of cells, not passing axons that are in white matter?
Really, the technical nuances of the VTA are really the white matter passing axons.
Okay.
So the way I think about a VTA is that it is really about the furthest extent you should expect for the stimulation to go outside of the area, kind of around your electrode, right? And usually what you're worried about are, kind of these relatively large diameter fibers of passage that are, they're not really associated with your quote unquote target.
Yeah.
So now I'm sure most users don't really understand that. They're thinking about it of, I'm trying to get my target volume or my target nucleus to be encompassed by this thing, but the proxy is really kind of the opposite of that. But once again, things become useful in clinical contexts for sometimes different reasons than what the original science is about. So, I mean, it's not a bad thing. Like I said, it is a very, very useful clinical proxy to accelerate an important, kind of clinical need.
Yeah, that's what Bryan tells me.
Yeah. So, but that's what over the years, okay, from a scientific perspective, there's many other things that we would like to be able to characterize, but a VTA kind of model is not really appropriate for that, right? Not the right neural elements, not the right trees relative to the electrode, right? All these things. A lot of great science going on in terms of, kind of simulating how electric fields, kind of activate different things around our deep brain stimulation electrodes. But unfortunately, maybe the clinical neurology literature isn't as, detail-oriented as I would like. And maybe people use these techniques to do analyses that are a little bit flawed. So.
Okay.
Yeah.
Sounds like I could steer you into something you might regret.
Yeah. Well, let's
following
keep
that
it
one.
politically correct. But anyway, but that's kind of like, that's part of what, if you want to be a scientist that is doing something that is going to be relevant to not just 10 other people in the world that care about your one thing, like you have to recognize that you need to build something that is generally applicable or generally useful to a much, much broader spectrum of people. And you're going to lose control of it once it's not, kind of like in your little lab anymore. And when it's out in the wild things are going to happen, and that's okay. Like, I don't get upset about it from the perspective of like, oh my gosh, this is stupid. But I do sometimes get, irritated that people are, doing things that are technically flawed in a very, inappropriate way, and then being publicly rewarded with, like publications that should not be published.
Yeah.
Right? So
And maybe high profile.
Exactly. That's very frustrating.
Yeah.
So.
At this conference that you were at and we were at with you recently, we brought up this idea of glial encapsulation. So that's this idea that you put a lead in, hopefully I've got it exactly where we want it. We do testing with stimulation, electrophysiology, confirm where we want. We get the optimal stimulation effect that we think, and then we deliver electrical current. And what I usually tell patients is, my goal is to not need these steering capabilities up front, because I want us to not have side effects that are that close. Mm-hmm. And something that I wonder is early on, you may start stimulating in different directions using the directionality. But if you want to stimulate later, if you have encapsulation like that, have you at some point, do you model a general field, or do you see there sort of being, for lack of a better way of putting it, I think of hydration shells around protein, so it's like a different thing, but basically having a fluid space between the neuropill and your lead, and then you stimulate out. And do you think that the way that the current spreads, or these spatial distributions, should be mapped differently if we have a patient we're trying to salvage because they're having too much side effect as their disease has increased and we've had to increase their current that we deliver? Is that something that should be taken into account?
Well, that's one of the benefits of the constant current devices now, is that really this whole like impedance thing shouldn't make that big of a difference. Mm-hmm. And I think we've proven that both in the biophysics and in kind of experimental measurements and in like real life practice. So I'm not worried about it that much. I think that once again a VTA and a clinical programming environment is it's a simple thing that's meant to get you going in the right direction. Whereas if you want to really do like the full on science experiment and you want to dissect how one neural population might respond to your stimulation parameter set compared to another nearby neural population that might have very different, biophysical characteristics to it, then, all these nuances of, kind of how you build up that model or how you build up that anatomy and, kind of stimulation, they make a huge difference, right?
Yeah.
And that's where we're at this really interesting kind of time, I feel like, in our kind of study of deep brain stimulation, because like we've answered a lot of the easy questions, right? Now we want to start answering these much more complex
I think
questions.
You're the one that's answered the easy ones. What? We is,
Yeah. But, and so if you want to be asking much more complex questions about networks or parallel stimulation streams of, kind of neural activity, like you really need to be thinking about like, okay, is the model that I'm using actually appropriate for the questions that I'm asking? And that's where there's, kind of disconnect, I think, and, kind of the use cases. So.
Yeah. Do you think that, so right now, we deliver, the most common thing would be something like 130 hertz square wave stimulation, regular impulses that are given through spatial pattern that's determined based on how it improves patient symptoms initially, and then where they would get side effects. Do you think that there's a role for starting to change patterning, and we'll talk to some of the folks about that later, but also having approaches where you deliberately try to deposit charge in one region and sink charge in another region with the shape of the current that you deliver? In other words, can you shape the recovery of charge around the lead in time, not just in space?
Well, the pulses that we typically use are so short, I'm not sure that would make a giant difference, in terms of the biophysics, but the train, kind of let's just talk about like, maybe the pulse trains and, you expanding our opportunity to explore that space, like that's what I'm really excited about for the next generation of, kind of some of the science experiments.
Yeah.
We can use that to one, just better understand the role of frequency, the generic role of frequency in the therapeutic effects of DBS, which is always, kind of one of these like little mysteries. But, not just the simple concept of, low frequency versus high frequency, but really this concept of, how do different patterns of either artificial neural activity that we're inducing because of our stimulus, or, the underlying, kind of stochastic neural firing that you just have in a normal physiological circuit, and can we figure out how to marry those two worlds together to actually like communicate with this circuit that we're modulating, as opposed to just basically trying to blow it up, right? That to me, that's the mechanism of DBS is blowing up the circuit that you're stimulating.
Yeah, you're turning an injury on and off.
Exactly.
Yeah, sure.
And so, but we're, learning so much all the time, maybe coming from all of these kind of crazy BCI type things, right? We're learning the language, if you will. Maybe we don't understand it because it's all in some giant artificial neural net of decoding, but we are learning something about the signaling patterns and what they mean. And if we can turn that on its head and then figure out how to actually like send information into the system, so a computer brain interface as opposed to a brain computer interface, right? Like we're not that far away from, being able to have some logical experiments conducted to make that happen, which is going to be super fun.
And do you think that, something that has gained a lot of attention over the last, decade primarily is this ability to insert genes into cells and turn them on and off with light. So you're capturing specific classes of cells. And something that I've wondered is, given that we have a heterogeneous population of neurons that we're interacting with, regardless of which structure that we're in, can we pattern the stimulation to select certain cell types?
Yeah. And
avoid the viral construct and all those things you need to do optogenetics, but can we just do that with the temporal pattern of electrical impulses that we give?
Exactly. So, the Gittes lab has shown that that's possible in rodents, and now, we're getting the first data from, human clinical trials of these concepts, and it can happen, and that's where you're tapping into not just, like a VTA or the way that people normally think about neurostimulation modeling is like, we're working on the 1 to 5 millisecond time scale of like knowledge, right? But techniques like you're talking about, you're thinking about using the kind of the intrinsic biophysics of the neuron itself and its synaptic plasticity components to kind of like help that neuron shut down or turn on or whatever, right? And it's just a whole other level, because now you're talking about manipulating the neuron not on the millisecond time scale, but you're using the intrinsic neural properties to manipulate it on the seconds time scale, right?
Yeah.
And then you're actually thinking about like, now you're really controlling things much more elegantly than like I said, the way we do it right now, which is just like blast the whole thing apart.
Yeah. Well, the idea of regular, I remember when I was doing my physics PhD, there was this idea about oscillations and signals. We measure brain rhythms. And my advisor and I were looking at data that we'd measured that didn't have a specific frequency range. And we measured, from that, we got this idea of broadband spectral change and power loss scaling and so forth in these brain signals. But the thing that seems odd to me is, and what we thought at the time, and it's because I didn't really know, I came as a physicist into neuroscience much more than the other way around. It never made sense that oscillations or that having a particular time scale would be where you would start. And it seems that we do know that you have systems where you have tremors that have regular frequencies, and we have epileptic activity that has regular frequencies, even if it's really high. And the natural thing would be, and this is some ongoing research that we're interested in, but just things that don't have a time scale at all, right? Where they may have something on average, but that, if you want to trick a neural population, you should trick it with something that looks like non-pathological
Yeah.
inputs, right?
Yes.
Yeah.
Yes. And you couple that with, okay, so that's, those are super cool experiments. Those are going to happen right now. It's all, like this is the 2025. But then you start coupling that with, like the whole neural recording side of things. And, and so you couple, local field potential, whatever control system with some kind of more elegant pulsing paradigm, man, then, maybe we're opening up a whole other level of our ability to kind of interface with the network, which is, that's always been the big goal. So,
yeah. And it seemed to me that over time you've moved, and this may just be my outside perception of the things that you're doing. And Bryan, I don't want to steal from all the questions if you're about to ask this, but you moved from being somebody who really looks at how you shape current and then say, well, if I give this kind of current on average, it should have this effect on tissue on average.
Yeah.
To instead saying, I'm really interested in understanding specific brain circuits and brain pathways that are involved with the areas that we think are relevant for disease, and really characterizing sort of specific pathways. And it seems like you moved really from the domain of what you're doing to the tissue rather than trying to understand it, to now you're much more focused on specific brain pathways and trying to understand specific circuitry.
Yeah.
Is that true?
Yeah, I think so. I mean, I still, my first love has always been the fundamental biophysics of, kind of electric fields and how they manipulate the firing of neurons. But those are 25, 30-year-old questions. Like, we're kind of done with that, like, so, the next level of question is really more about like, well, what are these brain circuits? How can we characterize them at the human scale? What are the right techniques to try and do that? A model is a proxy of, the real situation. We can't have real human, traditional neuroanatomy. It's just like not possible, right? So how can we characterize it? Well, to me, that was a super fun, or that is now a super fun engineering challenge. Like, how can we build anatomically realistic representations of, these pathways of interest in the human brain, and can you figure out ways to make that happen, with like super, awesome science level data that, you would never collect in a clinical environment. And then once you've built it in that kind of environment, can you figure out how to make it applicable to a de novo generic clinical patient, right? Mm-hmm. Those are the tricks. Those are engineering hurdles. Like, we know how we've got good ideas about how to build these kinds of tools in a scientific situation. But then once again, just like when Chris and I were first building the, kind of concepts of patient-specific DBS models, you also got to figure out how are you going to make it relevant to like an actual clinically relevant, situation. And that's the real challenge. And like I said, right now it's a methods, kind of evaluation. The concepts have been around for forever. Yeah. There's nothing novel about that.
Sure.
It's how do you make it work, on a scale that would be both clinically predictive, but also anatomically realistic. And we're not there yet, in my opinion. So,
what did you major in undergrad?
Biomedical engineering.
Okay. Bryan majored in computer science. I was physics.
Yep.
Now we teach people sort of neural engineering from the start.
Yeah. Right.
And it seems that, and you do a lot of things that are really important, actually educating neurosurgeons and neurologists and lots of other people about anatomy with the virtual reality tools you're creating and so forth.
Yep.
But just in terms of, you trained a lot of people that subsequently went on to do very important things in our field. Do you think that the approach of sort of starting with the nervous system in the beginning of your education, because that's what people are interested in, makes sense, right? Or do you need to learn the toolkit in a controlled environment, like engineering or science or physics, and only then start to learn the biology and apply it there?
Yeah, I don't know. So I was a super lucky person, for at least for this career path that I went in, because like I was a neural engineer, or being trained as a neural engineer from my sophomore year in college on. Like, it was just, that was the environment that I was in, was full of people that, like, I thought that was normal. Like, I didn't understand that. And when I was an undergrad at Case, I just was like, oh, wow, this must be the way everyone in this field works, right? And then you go out and you realize that, like, oh, wow, most of the people that are, using these commercial grade DBS devices, like, they don't have any training in this kind of stuff, like the physics of, electric fields, or the neural, kind of like biophysics or whatever, right? And so that's kind of an eye-opening experience. And, I guess it was good for me, because then it was like, there was a need for that kind of, like, someone who could provide some training, or some, or I could write papers about that and people would read them, kind of thing, right? So nowadays, like, there are many more opportunities, I think, for undergraduates to kind of go right into being what I would call a neural engineer. Most, 18-year-olds, when they're deciding where they want to go to college, haven't really figured out that they want to be that specific. So is there a trade-off? Like, yeah, maybe if you have such a myopic focus so young, you're going to miss out on, like, the broadness that if you just did a physics undergrad that you would get, right? And so I see it both ways, like positive and negative, I guess.
Maybe you could tell me about that race car.
Okay. Yeah. So this is a picture of your kids and my son, Leo, in my race garage, which is under my house in Raleigh. I guess maybe I shouldn't tell people that so they don't come steal it. But
Hold on. You have a race garage and then a normal garage?
Yeah.
Oh.
Well, I mean, like, my wife's car, like, she needs her own space and stuff, and, like,
It's pretty serious.
Yeah. So I've been, racing, as, like, my main hobby for basically my whole life. And so, like, once you get into it deep enough, like, like, some people have a horse stable and they have horses, right? It's the same thing.
Yeah, I guess.
Fair enough.
So I have, like, one of the great things about, moving to North Carolina was, well, one, it's such a great racing culture. It's a big thing down there. And then on top of it, the only way I could get my wife to agree to move was that we were going to build a new house and that she would design it and I would have no say over the budget. But the one thing that I did get to do was, integrate the race garage into our house. And so for, most of my life, I had, had a race garage that was, in some industrial park, basically, out in the middle of nowhere. And, and so now being able to have, my fun, like, literally, right below me at all times makes for a much more enjoyable, hobby kind of thing. So
Yeah.
and then the trailer, is kind of parked out front, and technically my HOA is it's not allowed, but no one ever complains. So yeah.
Film.
Yeah, I know. Well,
So how often do you actually take it out then?
So, well, like, in a normal race season, I'm probably, try to race, one, race weekend a month kind of thing. Like, that's kind of historically how I've done things. The peak of the season is in the, kind of spring and the fall. Summer, kind of, it's usually too hot. I mean, especially in the South, it's really tough. And then the winter, once again, it's a little too cold. And, race tires, they need to work in a very, specific operating temperature. And so, you kind of, one, it's for personal comfort. Like, the inside of a race car, in the middle of a race is like 120 degrees, and you're wearing, like, a giant thick blanket, jumpsuit or, race suit with a helmet on, and, like, it's hot, right? So, so it's, you kind of have to, as I've gotten older, I've definitely noticed, like, I can't take it like I used to. Yeah. So.
Okay. Yeah. Fair enough. There was a whole lot of trophies.
Yeah.
In there. Can you
Well,
tell me about
a lot of years. So, like, I only have to win once a year, and then it looks like I'm, really good. But yeah. So.
Okay. That's pretty good. I mean, it wasn't like it was like 30 or 40 trophies. So it was like more than once a year. I mean, impressive.
Oh, it's super fun, but like it's like a skill, and and when you've been doing it for a long time, you get better the more you practice, and so. But I have noticed, like, so I turned 50 this year, and from 30 to 40, like, no detriment whatsoever in skill. 40 to 45, like, plateau. 45 to 50, like, I can tell I'm getting slower.
Okay, so there's this movie coming out, right? And it's called F1.
Yeah.
I'm sure you know about it.
Yes.
Brad Pitt's like in his mid-60s, right?
Well, in the movie, I think he's only playing someone who's 50, but
Okay.
yes. Yeah.
Yeah.
But yeah, highly unrealistic. Yeah, that
Have you seen it?
would never happen. No. The movie, I hear the movie's great, and
Really?
I can't wait to see it. But highly unrealistic that anyone over the age of 30 would be brought into the Formula One environment. Like that is a complete non-starter.
What's the retirement age?
30.
Okay.
Yeah. Like Fernando Alonso is the only person who is legitimately, still one of the greatest drivers on earth that's older than that.
There's no like Roger Federer or
LeBron
James.
So you can still be a great driver. Like true pros can still be great from the age of 30 to 50. But what they do is they transition out of Formula One, and then they go and race what's called prototypes or sports cars. So 24-hour Le Mans cars, that kind of thing. So they migrate into what people would call the sports car world. That's the world I race in, is sports cars.
Okay.
So yeah, and over the years I've gotten to know a bunch of these famous pros, and it's
I bet
it's a very interesting life. Exactly, they have a life that we cannot understand. It's very different.
Yeah, sure.
I mean, not necessarily all good. Like, I don't envy their lives, frankly. Like, especially, like, if you're super, super great and you're famous, you're set financially, there's no worries. You're there to do your job, and you do your job well, and there's no worries, right?
Yeah.
But it's the guys that are on the fringe. Every day they are racing for their food, or their opportunity the next time, and there's no savings and there's no safety net, and like those guys, like I have just crazy respect for. But they're also crazy because they're like, this isn't really a very good life choice that you're making. So,
well, like tennis, if you're above about 100 in the world, or maybe 200 in the world, those guys are and women are just scraping by to get the plane ticket to go to the place. But if you're let's say you're the 3,000 number 3,000 soccer player in the world, I bet you're doing pretty well.
I bet you are. Yes.
So you got to get your kids playing soccer. I think.
Maybe that's the plan. Yes.
Yeah. Oh, good stuff. I have one other question I want to ask you, and the more lurid the details you have here, the better. Okay, this guy, your boss. Oh, it's
hard to see. So
Jerry Grant.
Oh, Jerry Grant.
He's one of my very close mentors and friends, and means everything to me.
Yes.
So the more lurid stories that you have, like if you have something I can hold over him at a neurosurgery meeting, I would love this.
The guy is a saint. Like, I mean, I've never seen him do anything, sketchy or questionable, and he's like the most helpful person in the world. So that's why I'm saying I think I have the exact same.
Yeah. But if you've got anything,
no, that's why I don't know. Like I'm sure everyone's got a dark side, right? Like I've never seen his. So yeah.
I don't think it's.
Yeah. But I mean, I
got a soft spot for pediatric neurosurgery.
Yeah, absolutely. Yeah. I mean, they're, you got to question their life choices in general anyway, right? But
well, I mean, my life choices. So, there's that. But
exactly.
Yeah.
But no, like Jerry and I have had a great synergistic relationship over the last couple of years. And basically, we both came into Duke at approximately the same time. And we really, kind of like, saw eye to eye immediately. And he really does believe in the value of engineers working, like in neurosurgery, he sees it, he understands it. And he's put his, the money where his mouth is kind of thing where, he and I have worked together to, make several key hires at Duke that I think are transformative, right? And he trusts that I am a good evaluator of talent, and he knows how to, grease the grease the wheels with the, the deans and presidents and whatever to say like, this is what we need. And like, we've just done a great job, I think. I'm really proud of that.
So having trained under him and spent a lot of time with him, and he took me under his wing, he still takes me under his wing, even though I'm almost 50 myself.
Yeah.
He's the kind of person that inspires you to try to do better and to be a better like human being and do good things for the world. And I think that, we're lucky enough to have Nuri Inche who joined us. He's a scientist that works with Bryan and I. And having solid engineers who get the importance of what they do for helping patients, I think is key.
Yes.
And, we're lucky to have you in our community.
Oh, I mean, I love it. The luckiest thing ever for me was, kind of like going to Emory and seeing what, clinical neuromodulation was in practice, and then realizing that like that was a niche and I could stay in that and, build a career around it. And then, like over the years, like maybe just because I just kept hanging around so much, like, feeling like I had become part of the functional neurosurgery community.
Yeah, you are.
It's awesome. I love
Yeah.
it. And so I wouldn't change anything.
Were you working with Bob down there, Bob Gross?
Yeah, so Bob was there. Aviva was still there right when I started, and actually, one of the the first DBS case that I saw in Emory, and kind of like had someone like directly explain to me like step by step, this is what's going on, kind of thing. That was Aviva.
Yeah, she's awesome. We have some work we do together related to brain-computer interfaces, and it's more editorial kind of work and talking about different things. And she's been, for me, a really wonderful influence. She's actually Nuri Inche. All the science that he did when he started was with her.
That's right. Yeah.
And Bob unfortunately left Emory and went to New Jersey. And he's doing well, but he is at Rutgers. He's a chair there.
Yeah, I know.
But I mean, he like I've called him, sort of in those times when you need somebody who's frank about what to do in that clinical situation, and he is. He's done a lot for the field.
Oh, yeah.
The guy's awesome.
Oh my gosh.
Yeah,
Yes.
totally awesome guy.
Yeah, absolutely.
Anything else you want to ask Dr. McIntyre, Cameron? We got our steins here. This is awesome, and with water. Yeah.
Yes.
What do you think is going to be the next, frontier here? That's going to push us forward. I know you talked about the kind of different stimulation parameters and tracking how that affects things. Is that kind of what you think, or is there going to be?
Well, I think from the science perspective, I think, kind of like this next generation of understanding of the intimate neural circuitry that we're getting at, right? And so, but we need to build the neuroanatomy foundation first that doesn't really exist. And then we'll be able to do, kind of the clinical connections or the, kind of therapy connections to this network or that network, right? I think all of that stuff is very premature right now, but we're going to get there. I think that, on the engineering front, like we will learn how to explore this parameter space in much, much more elegant ways. And that is really, in my eyes, this is one of the main powers of the whole AI revolution and how it will help the field of deep brain stimulation. There are literally, it's an infinite parameter space, and, there's no way that we don't know the language and we don't know the logic of how to search that space right now, in my opinion, right? Yeah. We have good ways that we can kind of ping the system, if you will, with single pulse or whatever. But the concept of really being able to understand the interaction between this infinite parameter space of stimulation and its subsequent recording feedback, like AI is going to be instrumental in making giving us direction on where to go with that, because like I said, we don't know how to, we don't know the language and we don't know how to efficiently explore that space. And so that's where we'll get there, though.
Yeah.
So,
yeah. Good. Well, it's great to have you with us. I'm really happy that you're able to join us, and we enjoyed having you at the meeting as well. So thanks for coming such a distance.
Yeah, we're looking forward to having you back soon to the STEIN headquarters.
Sounds
undisclosed location.
Yes.
In Rochester, Minnesota.
Yes, absolutely.
Awesome. Well, thanks.
Great. Thank you. Yeah.
good to see you.
Yep.